Welcome back to General Statistics. In today's lecture, we're going to do an overview of the topics on Exam 2 and do a quick but detailed summary of each of the chapters, and then we'll look at some example problems. Before we move directly into the first topics in this section, namely correlation and regression, I'm going to review very quickly a couple of essential things from the previous section that I can see a lot of you are still struggling with, or that really bear repeating because they certainly could play a role in questions on this exam or be tested directly, and as a minor emphasis, but you'll see what I mean. There we go. In a moment. First, we talked about research design and the kinds of conclusions that you can draw based on the research design that you've utilized. We have two major categories: experiments and observational studies and surveys. When you do an experiment, namely a controlled experiment or a randomized controlled experiment, then you have the opportunity to potentially draw causal conclusions. We will look in our next unit at some of the ways that you determine if there is a causal relationship in an experiment, but only an experiment offers us the option of drawing causal conclusions. We collect a lot of data, however, and do lots of research through observational studies and surveys. This kind of research can give us lots of different insights, and they're centered around these four topics listed here. We could get insights related to the association between two variables, difference tests. We could look at the difference between groups. We could look and see if two events or attitudes, two different things, are independent, and we can make predictions. We can apply these same tests in experimental data, but it just certainly bears noting that you can only draw causal conclusions when using these tests in an experimental setup. We talked about levels of measurement, and these are so important because you use the level of measurement of a variable to help you decide what kind of test to do. So we talked about three primary levels: the nominal, ordinal, or interval, and we have combined the interval ratio. And most people are fine on identifying nominal variables. But remember that a nominal variable is anything with just categories. There's no ordering among them. You could have more than just two categories. There could be 3, 5, but there's no clear order. An ordinal variable, you have now order within the categories, but there's not necessarily an equal interval between the points. And there was a lot of confusion about this in your Lab 1 reports, I noticed. So this is why I'm highlighting it. Some examples of some ordinal variables are things like strongly agree, neutral, disagree, strongly disagree. You see there's an order there. It's an ordinal variable then. And anything where there's an order to the categories is an ordinal variable. And this is important, so important to remember. Age could be, depending on how it's measured, an ordinal variable or an interval variable. So if you just measure age in even intervals since birth, say years since birth or months since birth, then you've got an interval variable or an interval ratio level variable for our purposes. But if you have classified age into groups like 18 to 34, 35 to 46, and so on, to 65 plus, like they do in the GSS data set, that's an ordinal variable. Why is this important right now when we discussed this before? Because you will need to decide in some based on some research examples or examples of variables, you'll need to decide if correlation or regression is appropriate for those variables. Well, correlation and regression are only appropriate when you have an interval ratio level variables. And as we add in more tests, as we're going on in the very near future, this is increasingly important. We also have independent and dependent variables. It's important to remember these, and we'll come back to this in the context of regression, the predictor and outcome variables. The third variable comes back in because we, in correlation and regression, really must be aware of confounders, and in regression, we come up with ways to address this. This is an example of bivariate and multivariate statistics. Now, you'll see on here, we haven't done some of these tests yet, but we will. There's no need to fret about things we haven't done yet. Don't worry. You'll have time to learn them when the time comes. But for now, remember that if a question is asking you to find the association between two things, most likely this is about correlation. However, if you need to predict scores from some other scores, that's going to be in the area of regression. And as you can see, these other tests, like a chi-square, it doesn't offer prediction as an option. They are mutually exclusive categories. So this is a useful way to start thinking about the different procedures that we encounter. In this unit, we first did a little overview in Chapter 7 of plotting lines and points. We looked at the algebraic equation for the line, and this is the same as the equation for the line that we encounter in regression and correlation. This is for a linear straight line, and it's always y equals mx plus b, or y equals the slope times the x variable plus the intercept. The slope is always rise over run. We come up with a couple different ways to describe rise over run, but there's always this basic format going on. Remember this, when you plot lines, you only need 2 points to plot a line. So you could be asked to draw a conclusion from plotting a line if you're given the intercept that gives you 1 point and one other point, or the intercept and the point of averages, for example. So you only need these 2 points to plot a line. It doesn't matter if you're just given the points or if you need to use some logic to remember them. Just remember, it only takes 2 points to make a line. In Chapter 8, we got into formal ways to look at association between variables, namely correlation. First, scatter plots give us an indication of the linear association between variables. A scatter diagram is summarized by 5 statistics that you need to be real familiar with and understand. The average of the x values, the standard deviation of the x values, the average of the y values, the standard deviation of the y values, and finally, the correlation coefficient, or R. We can't just look at one of these and presume to have fully described the data or the scatter diagram. We look at a couple of things about a couple more things when looking at a scatter plot, including the direction of the association. So we first examine whether the association is positive, meaning that the cloud slopes upward, and as one variable increases, so does the other, or a negative correlation, which shows that as one variable increases, the other decreases. We see this translated into the correlation as a positive value or a negative value. We also examine the strength of the association, and that's helpful. This can be helpful in prediction when there is a strong association between two variables. But if there's only a weak association, then you can't get very good quality predictions. So your prediction is going to be a lot more accurate the stronger the association or the higher your R value. These are examples of scatter diagrams and their prototypical look. As you can see, when we are looking at just degrees of correlation or degrees of association, they go from just a random array to being increasingly packed in a line format as you move from a low association to a perfect association. We also have a couple of different ways to characterize the type of correlation. A positive or negative correlation, as I described. This is showing our cloud sloping upward and downward. We also talked about a couple of types of nonlinear association that will come back up as we're looking at correlation and regression topics. And for example, you could see a nonlinear association look like a curved, or this could be called a curvilinear array, or this is a partial correlation. The variables are correlated to a point and then not so much. The correlation coefficient gives us a measure of the linear association, or the clustering around the line. Thus, we would expect, as we look along here, we're going from a correlation of about 0 here to, maybe 0.3, 0.6 or 7 to a perfect correlation. So there's a direct association between the correlation and the clustering around the line. Note that when topics show up more than once in the slides, that means I think they're really important. I know they're important. They show up a couple times because I probably saw multiple questions that they were used in, or something similar to that. So just remember these descriptive statistics and how you can use them, and we'll discuss this a little bit more because we come back to them again another time too. The correlation coefficient always ranges from -1 to +1. So if you are presented with a correlation coefficient of 1.6, that's impossible. If it's -2, again, impossible. They just cannot happen. So that there's a problem there. And the range for the correlation, anything in the negative side is indicating a negative association, and the positive side tells us our variables move together. The standard deviation line always goes through the point of averages. And we can describe the slope of the standard deviation line by just looking at the ratio of the standard deviation of y to the standard deviation of x. This is what I'm looking at here. And this should look familiar to you already because it's very much like how we could measure the slope of the regression line. But right now we're talking about the SD line. So the slope here, remember this just looks like when you map it into a fraction, and you just assign a positive or negative value depending on whether your association is positive or negative. Finally, to calculate the correlation coefficient, the process is to convert each variable to standard units and then take the average product. I know we discussed how to do this in Excel. You should still be familiar with the basic process for how the correlation coefficient comes to be, especially as it relies on the standard units, because we encounter standard units in many, many places throughout this course. We already encountered them in the normal approximation, i.e. the z-scale. Standard units are also units of standard deviations, and they are a very helpful unit. And like this is as standard units, it's a pure number, which we'll discuss in a moment, that's not affected by changes of scale. So you can change the scale of one of your variables, and that's not going to affect the correlation coefficient whatsoever. Notice that on figure 4 here, we see a positive correlation. And as R gets closer to 1, the distance of a typical point above or below the SD becomes a small fraction of the vertical SD. So there's, somewhat more spread when you are have a lower correlation. And if we have an R that's closer to 1, this would be a smaller oval here and have a smaller distance. Oops. The only point I want to make here about our standard deviations is that you can have two studies that have the same correlation coefficient, but that doesn't mean that their variables have the same standard deviation. And you can see that outlined here because both of these diagrams have the same correlation coefficient, but they clearly have different standard deviations for each of the variables. You can see that in the spread. We discussed some exceptional cases where you can't use the correlation, namely when you have outliers or a nonlinear association. And we remember there's other problems with a nonlinear association. So these problems, these exceptional cases, are echoed in regression. We also discussed how ecological correlations are correlations that are based on rates or averages, and like infant mortality rate, death rate. These are so common in social research and in health research. And the problem specifically with ecological correlations is that they can be misleading, and specifically, they tend to overstate the strength of the association. And that can be quite problematic. For example, overstating the association would make us think that there's a much stronger relationship between two variables than there is in reality. And finally, association is not causation. This is a very important thing to remember. We must have a controlled experiment in order to draw causal conclusions. So remember that a controlled experiment is prospective. People have been assigned to groups. They were exposed to a treatment or maybe a placebo or whatever the usual treatment is. There's different ways to approach the levels of the independent variable in an experiment, but the key thing here is that the participants are randomly assigned to groups, and it's prospective. Observational studies are retrospective, people reporting on their behaviors in the past, their general beliefs, which are still really behaviors in the past. So when we're dealing with observational data, we have to be very careful about our conclusions. We can only see association. We can describe that as X goes up, Y goes up, or Y goes down. We can't say X causes Y. The main reason we can't say X causes Y is because of confounding variables. An experiment that's controlled and randomized based on potential confounders allows us to address confounding of variables in the experimental design. But this is very hard to do in an observational study. And since we can't account for possible confounders, we really can't draw causal conclusions. And we can make some attempts to control at confounders through multiple regression, which we discussed just a little bit, but by and large, we can't sufficiently account for them to get at causation. So remember this, the calculations can't protect you from errors in logic. You can do calculations on any numbers you want, but if you're not using the right numbers for, based that are statistically valid, then and sound, measure, sensible, your data is similarly invalid and unsensible. So you really have to be careful to look at variables to look at associations that make sense, and to think about what is really being studied here. Not to mention also the basic aspect of remembering that you have to use certain levels of certain procedures based on the level of measurement of your variables. In chapter 10, we break into regression. General goal of regression is to explain why variables vary. We can quantify the relative importance of any variable, but we get through to this through the regression equation. Regression describes how one variable depends on another. Thus, the regression line is for y on x, which estimates the average value of y for each value of x. To put this in another terminology, we're regressing the outcome on the predictor. It's important to remember that and to have mapped your outcome and predictor variables in a sensible way. With each increase of one standard deviation, there's an increase of only r standard deviations in y, and we use this to help us find the slope later on down the road. The regression method requires that the variables are measured at the interval level, that there's a straight line relationship between the variables, that the samples were chosen at random. This is important. And also that both of the variables have a normal distribution. We've looked at a variety of calculations related to correlation and regression so far. We have our 5 key descriptive statistics: the standard deviation and average of x, the standard deviation and average of y, the correlation coefficient. We also have the slope and the line equation, and we need to get back into our descriptive statistics to remember what we can do with our different standard deviations. So the standard deviation of x just helps us gauge changes in the x variable alone, whereas the standard deviation of y gives us just a general change in y without accounting for x. If we want to look at them together, then we need to look at the association in standard deviation units, or the slope. We can again map out as the standard deviation of y over the standard deviation of x and multiplied by r. Oops, just thinking about r. There we go. Y only goes up by r standard deviations. These are the units that we use to describe the association. And you see it here mapped out. the graph of averages is helpful in a couple of ways. We can remember that the regression line always goes through the point of averages. So the point where you've got the average of X and the average of Y. Another way that the averages come into play in our graph of averages is to help us look at nonlinearity. So if you have a nonlinear relationship, which we can, then we can use the graph of averages instead of using the correlation. Because remember, when we have a nonlinear relationship, we can't use the correlation. We can't use the regression line. So what do we do if we do have a nonlinear relationship? We have to do something. There's many other some things, but for our purposes, in this class, we're going to just say, well, if it's nonlinear, we're going to rely on the graph of averages. Finally, how do you decide between correlation or regression? First, you get a graphical representation of the data, e.g. a scatter plot. In this way, regression has a lot of similarity with correlation. This is the first step for both. Both help you get at the strength of the association, but only regression specifies the nature of the relationship, and their calculations are the same. In addition to having the same assumptions too. The regression line, however, fits a line through the scatter of points, whereas Pearson's coefficient, or the correlation coefficient, measures the degree of fit, the degree that the points fit the line and cluster around them. So these are nuanced but different. The regression line, as we'll see in our next section, is going to be the line that minimizes the error, that has the least squares error through the scatter of points. Less specific, it just gives us a general measure of the degree of fit, but a very useful measure. To interpret the regression line, remember that the y-intercept A is the predicted value of y when x is 0. So the y-intercept is technically the point 0, A, where A is whatever the y value is. And remember, to plot a line, we only need 2 points. We could use 0A and the mean of x and the mean of y. The regression coefficient gives change in y for each increase in x. And remember, your y-intercept value may or may not be meaningful. So if it seems not meaningful or nonsensical, that's maybe not a big deal, depending on your data. There we go. In our next unit, we look at the RMS error for regression. Error is a very important topic. It's one that we revisit over and over in statistics. And the reason it's so important is that chance error is always there in the measurement. There's always chance error in your variable measurements. But we can't measure that chance error directly. If we knew specifically always how much chance error there was, then we wouldn't need all of these different ways to account for error, to measure deviations and things. But we can't. Thus, we have to come up with the most accurate ways we can, or use the most accurate ways we can to measure error. And in the case of regression, we'll use the root mean square, which is a very useful measure of error. And we'll see we're going to be doing a lot more with error in our next unit because we have to estimate it. The regression method, which lets us we can use to predict y from x, we have to always remember when we make our predictions that they're going to be off a little bit. It's just a prediction. How much is the actual value going to differ from the prediction? That's the size of the root mean square. So we can estimate the overall size of the difference, between the prediction and the actual value by using the root mean square error. And you see here that when we're talking about prediction error, we're specifically talking about the vertical distance from the line. Okay, error goes vertically because the error is in the y-axis. Remember, this is always x and this is always y. So for our purposes, so the error is always in the y prediction, or is to quantify the y prediction error. So it's the vertical distance from the line. This is an important point to remember. When we map the error, the RMS error, onto the regression line, we can see that the error percentages take on a similar distribution to the normal approximation. As you can see about the line, within one error term above and one error below, you've got 68% of the distribution or of the points, which although we are looking now at two distributions, right, of the points, within two RMS errors above and below the line, we've got 95% of our points. And this corresponds directly to the proportions or percentages that we see when we are looking at a normal distribution and using the standard scale or the z-scale. And there's some good reasons why there's this similarity. The standard scale is in, remember, standard deviation units, and the standard deviation is just the root mean square of the deviations from average. So there's a good reason that these are similar topics. However, the SD of y, we can only get the SD for individual variables. So it's a measure that we can only assess for the x variable or the y variable independently. And the SD of y tells us how far typical points are above or below a horizontal line through the average of y. So if this is the average of y, here's our horizontal line. And it's just telling us how far above or below things tended to be. So they call this the baseline method, and it ignores the x values, which makes it a pretty poor predictor. I mean, it's okay half of the time if you need to guess the average of something, if you need to guess the score of someone drawn from average and only know you don't have any other information about them, then you should guess the average y value. You'll be right half the time. But if you want to be more accurate than that, then you need the x variable. And when we add in the x variable, then we can use the RMS error to get a better quantification of how much that prediction of y is going to be, to help you get a more precise indicator of y, taking into account x. And then if you want to get even more precise, you can use the RMS error to further refine your prediction, or to at least give you a confidence level in it. And the units for the RMS error are the same as the units for the variable being predicted. Just remember, the RMS goes vertically. And the error for the regression line is, as we said, smaller than the standard deviation of y, but we need to take into consideration the standard deviation of y in computing the RMS error. It's equal to the square root of 1 minus r squared times the standard deviation of y. And this is just telling us how much smaller the RMS is than the standard deviation of y. The RMS, and you can see that R comes into play all over the place here. We've talked about 3 primary uses for R that you should remember and feel really comfortable with. R first describes the clustering of the points around a line, gives us a measure of the degree of fit relative to the standard deviations. R also says how the average value of y depends on x, as in associated with each SD increase in x, there's an R standard deviation increase in y. So, and finally, R helps us determines the accuracy of the regression predictions through the formula for the RMS error. We can call the RMS error, the error is also called the residuals. This is a very common terminology. And the residuals from the regression line always average out to 0, just like the mean deviations from average. The mean deviations always average to 0 also, because the error above and below the line is the same. You would plot the residuals. The reason that we plot the residuals and that this is a common procedure is that you need to examine the pattern of the residual plot. If there's a pattern that you see, that's a sign that regression is not appropriate. So in summary, we use plotting the residuals to help us assess whether or not regression is an appropriate test. If there's no pattern, then regression is appropriate, or may be appropriate. However, if there is a pattern, this is a clear sign that regression is not appropriate. We also looked at these vertical strips and described them as either homoscedastic or heteroscedastic, meaning just if they're homoscedastic, that the dots have the same or homo spread, which scedastic is just another fun word for spread. It rhymes with elastic, which also, it stretches, but there's a similarity there to help you linguistically. When all the vertical strips have a similar amount of spread, you can say it's homoscedastic, and you're safe using your regression equation and RMS error to make predictions. And we can see that this is showing us a similar spread, that spread being a normal distribution, and you can see those distributions plotted here for the 2 different strips. And the important part is not the most important part of this diagram on the right is that the histograms have similar shape and their standard deviations are almost the same. When it's heteroscedastic, there's problems because the regression method is off by different amounts in different parts of the scatter diagram, so you can't use the RMS error. And a final point here about the error and vertical strips, when we are working inside a vertical strip, we can use the normal approximation to help us predict specific probabilities for points within the strip. But this does require homoscedasticity. One more bit of regression left. Well, let's do a little overview of the regression line. So we've kept coming back to the slope and intercept, and we can always conceptualize it as rise over run, but when we think about this in the context of regression, we should think about rise is equal to the R times the standard deviation of Y, and the run is the standard deviation of X. With this whole thing, both of them being equal to the slope. And you see that illustrated here in the figure 3. Why is the slope so important? Because it's a key part of the regression line equation. You should be able to find the slope based on different scenarios similar to exercises that we did in class, and be able to use the regression equation to make regression predictions by substitution. Remember that if you run an observational study, or if you're using observational data, like for example, the GSS data that we've looked at in lab, the regression line only describes the data that you see. So you can only make predictions about folks similar to that population. And you can't use the line to predict interventions or to say, well, this population is different from another one, so I could use these predictions to draw conclusions about what if something, if population A adopted the same practice as the other population, would they change too? No, this is lots of extrapolating. If you're thinking, well, that extrapolating doesn't make sense to me, well, that's good, because it does not make sense, is what I'm saying. You can't extrapolate beyond the data that you see. So you should be thinking, if you're asked, can you use this information to predict about some other interventions or sample populations? The answer is always going to be, no, you can't. We get a little introduction to the method of least squares. This is mainly important to help us remember that among all the lines, the one that makes the smallest RMS error in predicting Y from X is the regression line. This is how the regression line is different than R. R is just giving us the degree of fit of the line, not the line itself. The method of least squares helps us get the regression line, and it estimates, the least squares estimates always minimize the root mean square error. And the key point here to remember is that you always want to minimize root mean square error. A study that has a line that has a model that has a bigger RMS error is a worse model, objectively speaking, than like statistically speaking, I guess we should say, it's a worse model than one where you got a smaller root mean square error. Okay. it's important to remember to ask yourself, does this regression make sense? The way to assess that is to first assess, was there any sort of nonlinear association between the variables, or a partial association as we saw? If so, you know the regression line is quite misleading and probably inappropriate, thus the regression does not make sense. And if the association does look linear, you have to ask yourself, does the regression make sense logically? Is there logic in regressing a variable x on variable y? And do the outcomes make sense in light of the regression fallacy, where repeated testing tends to lead to regression to the mean, or doesn't lead to regression to the mean, but the phenomenon of regression to the mean is observed across repeated testing with the same participants. And finally, we get a brief overview of multiple regression. And although you don't need to do any calculations for multiple regression, certainly at this stage, although it's very much the same essentially as regular regression calculations in many ways, we should be familiar and comfortable with the general regression equation and the multiple regression equation as which is just a small extension of the regular regression equation. And so we can see, let's map out here, we had our standard regression equation where y equals the intercept a plus the slope, we'll call it b here, times the x variable. In this case, now that we have multiple regression, now we have more than one x variable. So this is our x1 variable, educational level, and S, parental status, would be our x2, our second predictor. So that's the difference when you're doing multiple regression, is that instead of just having one predictor variable to help you account for change in y, you have more than one predictor variable. And each predictor is treated in the same way. It has a slope and a place in the equation, which is what we see here. This slope, C is also a slope, but it's the slope of x2 on y, the slope of x2, or of y on x2. So standard format, but just the addition of the additional predictors. We could also have in here an error term, which you commonly see in regression equations in the real world. You would see one other term, which is the error. You could see more than one other term, but this is often, even in simple models, presented with this addition here. In summary, when we have regression, we have descriptive statistics, including the slope and intercept, that are both essential to the regression method. And we can use the correlation and the standard deviation to find the slope, and you should be able to do that in your, easily, and to help you solve other problems too. We use the line equation to make regression predictions. We can only predict the outcome variable, not the predictor variable. If you're asked to use the regression line to predict the predictor variable from a y variable, that's a different regression line. So you'd have to use that other regression line to do it. And finally, the least squares line is the one that makes the smallest RMS error in predicting y from x. It's the regression line, and the least squares estimates are just the slope and intercept of the regression line. We look at scatter diagrams one more time to remember to examine them for homoscedasticity, or a football shape in the distribution of points, to tell us whether or not we can use the average and standard deviation of the two variables, and R to measure the strength of the association. If this diagram is homoscedastic, then you're free to use your descriptive statistics. But if it's not, then you have to use other methods. For example, maybe the graph of averages. Controlled experiments versus observational studies. I know we've talked about this already, but it's so important to remember that you can only say that you have a causal connection when you've done an experiment. So language that sounds like a causal connection is that isn't just R cause or X causes Y, but might be X leads to Y. Well, X leads to Y, this is the same meaning. We can really only say that an increase in X is associated with an increase or decrease in Y. We can quantify the amount of the increase or decrease, but we cannot say that one leads to another. And always remember that nonlinear relationships have their own special adaptation of procedures. So you can't use the correlation and regression. You could use the graph of averages. That's really a scatter plot and the graph of averages are really the only things we can do with a nonlinear relationship at this point. And that's everything on regression that we're going to cover. And that isn't everything that we covered. It was just a summary of the things we covered, but a summary that includes the topics that are pertinent on the exam. So if I left something out of the summary of correlation and regression that we just went through, that should be assigned to you that it's not on the exam. So you shouldn't spend your time studying it. I would really recommend focusing on topics that I've introduced in this lecture. Is every single item, have I mentioned every single item? Probably not, but by and large, the vast majority, certainly anything that's in complexity beyond what we covered today is too hard for the exam. The exam is sort of at the middle level of the hardness of our relative problems. I don't write your exam to make it the hardest problems possible, just to try to make them easy or middle problems for you. So we are going to look so briefly at probability, but we're going to do this, go through a couple of our probability topics quickly. Now, if you want more coverage of probability, the videos on the topic are available, and there's just brief videos for each chapter 13 and the review exercises of 13 and 14. They're short videos anyway, but they go into a little more detail than we're going to today in terms of examples and applications. We start out remembering that we've taken a broad frequency interpretation of chance, meaning basically that probability is measured by frequencies. For our purposes, there are other ways to quantify chance and probability, but we don't have the space in this course to, fully expand on everything in probability. We're just looking at things relevant to where we're going after this unit. So you can measure a probability generally by the number of favorable outcomes out of the total possible outcomes, or the number of, you could say, favorable or outcomes of interest out of the possible outcomes. This is for an individual event, and we're going to look in a moment at what we do when we have more than one event. And always remember that your probabilities are always between 0 and 100. And the probability or chance of an individual event or a group of events is equal to 1 minus the chance of the opposite thing. So this sounds basic, but it's actually a real important application. A number of your examples in the book discuss drawing at random from a box. The key points here are that you can draw at random with replacement. So when we remove the 3, we replace it, or we can draw from the box without replacement. And in that case, our second draw is got a smaller number of possible outcomes. And that shouldn't. It's important to remember that conditional probability is the probability of an event given that another event has occurred. And we're going to think about this more in a minute, but the main point here is that conditional, things that are conditional, the events are you've got the probability of an event given that another event has occurred already. So conditional probabilities, you might be asked, this comes into play if you're asked about like the probability in a second chance, like we see here in B, you turn over the first card, it's the 7 of clubs. Now what's the chance of the second card being the Queen of Hearts? It's conditional because the condition is that they go in this order. The multiplication rule is the chance that two things will happen. It tells us that the chance that two things will happen equals the chance that the first will happen multiplied by the chance that the second will happen, given that the first has happened. So you can see here that this first point, and that generally the multiplication rule applies to conditional events, or unless you have other information, you should assume that you should assume and use the conditional probabilities. And we're going to look at this in a little more nuance in a moment. Because we need to take into consideration when we are looking at two events, whether they are independent events or dependent events. In an independent event, the chances for the second, given the first, are the same, no matter how the first one turns out. The events are completely independent, like the 2 tosses of a coin, or however many tosses of a coin you want to make. They're always independent tosses. In dependent events, the chance of the second event depends on the outcome of the first event. So you can consider two things independent if you've got the same chances. The chances for the second event stay the same no matter how the first one turns out. But with the dependent events, the chances of the second event are going to be directly dependent on the outcome in the first event, as in drawing without replacement from the box. So when we draw without replacement from the box, the draws are dependent because once you take one number out, that number is no longer available as an outcome. And we'll get a little more clarity about that in a moment. Events can also be considered mutually exclusive. Now, this is a special category where the occurrence of one event prevents the occurrence of the other. One excludes the other. They can't both happen. I like the good example of this where it's a nice criminal justice example. When someone is charged with a crime like murder, that for that specific crime, they might there's possible charges. They could get a murder charge. It might get plea down to like a manslaughter charge, etc. So there's a set of possible outcomes, but the occurrence of one prevents the occurrence of the other. If you're charged with murder, you're not also charged with manslaughter. These are mutually exclusive, or sentenced to murder. Manslaughter, I think that would be true for either case, but only one of them can happen. And if you want to find the chance that at least one event occurs, and the events are not mutually exclusive, you can't add those chances. So you have to multiply them, and we're going to talk in a minute about discriminating between these different independent and dependent conditional probabilities, all these different types of events. But we need to learn one more rule, which is the addition rule. The addition rule specifically applies to mutually exclusive events. Well, this is helpful because we can generally identify mutually exclusive events, and when you can identify them, you should add the chances, and that's going to be the best estimate of your probability. If you add chances for events that aren't mutually exclusive, then your probabilities will get way too large and it won't make sense. So now, what is the difference between mutually exclusive and independent? When events are mutually exclusive, the occurrence of one prevents the other event from occurring. It can't happen together. A baby can't be born a boy and a girl. They're mutually exclusive. In independent events, we have a situation where the occurrence of one event doesn't change the chances for the other. And of course, the converse is true too. For dependent events, the occurrence of one does change the chances for the other. So when do you know to add and when to multiply? Well, you need to consider what sort of chance you're trying to find. So to find the chance that at least one of two things happens. So at least one of two things, you can add the probability of the events, and this does require that the events are mutually exclusive. But if you need to find the chance that two things both happen, then you can multiply the events. And when it's further important to remember that you use the unconditional probabilities when the events are independent, but if the events are dependent, you use their conditional probabilities. And we'll do a few probability examples that will represent the scope of the application. We'll look at this on the exam. We're still going to keep a pretty surface discussion here. So this is the basic summary of our issues in probability. You need to know the multiplication rule and the addition rule. When do they apply? And especially the independent and dependent events. That's an important distinction that you should be able to understand when an event is dependent or independent from simple examples. Okay, so now we're going to take a brief break and come back and do some problems related to these topics. But again, this is given us a general overview of where to go and what to look at of topics to expect in our main areas, correlation, regression, and probability for the next exam. May the odds be ever in your favor.